Okay, so molar energy bridges are really powerful. So how do we calculate them? Well, we calculate them through understanding heat capacity, and we enact this experimental process called calorimetry. So I'm going to explain the general concept behind calorimetry, but first we need to understand what heat capacity is. And the definition of heat capacity is that it's the energy required to raise an amount of a substance by 1 degree Celsius. So if we know the heat capacity and we observe a temperature change, then we'll be able to infer the energy. So it's a way for us to get at energy information. Okay? There are two versions of heat capacity that you'll see. Okay? First is the molar heat capacity. It's given the symbol C, and it'll have units of joules per mole degree Celsius. Okay? Now, if you look at C, right, it is proportional to energy. It's proportional to joules. So if we're given a C, we can kind of think about how the definition fits with these units, right? As C gets bigger, right, that means the energy required to make something hotter, the energy required to raise something by 1 degree Celsius increases. Water has a pretty high heat capacity, all right? Where some objects like a metal, like aluminum, would have a lower heat capacity, okay? If something heats quickly, that means it takes less energy for us to get a degree Celsius change. If something takes a while to heat, then that means it takes a lot of energy to make a degree Celsius change, okay? So hopefully how you can see now if we look at the units that the heat capacity is proportional to that energy, all right? The specific heat is also a heat capacity, okay? So you'll see this labeled as specific heat or specific heat capacity, and really it's the exact same thing. If you notice the difference between these two objects though, what changes is how the amount of that substance is quantified. For a molar heat capacity, all right, we have joules per mole degree Celsius in terms of the units, all right? And for a specific heat, we're looking at the energy required to raise a gram of a substance by 1 degree Celsius. But notice it's proportional to energy, all right? And then also realize that this looks like a fraction. So after we discuss calorimetry, we're going to use this almost like a conversion factor. Again, there's energy information here we'll be able to acquire if we go on and think about isolating joules, right? Before we get there, how do we utilize heat capacities? We do this thing called calorimetry, okay? So this is a simple drawing of a calorimeter. And actually, if you look at slide 3 in your chapter 5 slideshow, all right, you'll see a sort of a better schematic of what a calorimeter looks like. These are generally what we call coffee cup calorimeters, because the whole idea behind calorimetry is we understand that things can have different temperatures and they can exchange heat. So calorimetry is always about running an experiment that monitors heat exchanges. So a calorimeter, and the reason why I call it like a coffee cup is, the reason a coffee cup is easy to hold is because it's hard for heat to escape it. And in fact, if you would take like two styrofoam coffee cups and put them together, right, your hand wouldn't really feel like the coffee cup was hot or cold. Heat wouldn't be flowing into your hand. All the heat would be exchanged inside that calorimeter. Now, calorimeters generally, are filled with some liquid, and normally, especially for us this semester, it's water. And then there's a stirring mechanism inside it. And then there's a thermometer to monitor the temperatures. And what we generally do is we have some sort of process or object that's going to generate heat. And what we monitor is the temperature change of the water. So if all the heat is sort of exchanged on the inside here, then heat flows from the hot object inside here to the cold object, right? And so one thing is losing heat and one thing is gaining heat, right? Those heats would be equal in magnitude but opposite in sign. And so whenever we read a problem and it looks like we're dealing with a heat exchange, the starting point for any sort of heat exchange problem is this calorimetry starting point. Minus Q loss equals Q gained. So if I put something hot in here and it's around colder water, just as an example, heat's going to flow from the hot object to the water. But when does it stop flowing? Well, by the definition of heat, we run into this thing where we understand that heat flows until a temperature difference is nullified. Heat flows until all the final temperature, so T sub F stands for final temperature. Heat flows until all the final temperatures are equal. So often a problem looks like, hey, something has a heat capacity. I put it inside a calorimeter. That heat capacity is going to allow me to figure out energy. Well, the energy lost in the form of heat is equal but opposite in sign to the energy that's gained in the form of heat. Okay. Now, before we get to one other thing. Calorimeters also have a heat capacity. Now, we call this the calorimeter constant. But essentially, a calorimeter is made with a stirrer, a thermometer, certain walls. It has objects that each themselves will gain some heat. And if we understand how that heat is gained, right, how that energy is gained, we can develop this calorimeter constant that allows us to monitor changes in temperature and infer energies. Calorimeter constants don't have moles or grams in them, but notice they kind of have the same setup. They have an energy in a degree Celsius, an energy in a degree Celsius, and an energy in a degree Celsius. We don't really have to put a joules or grams down here though, because we always use the same amount. For something like specific heat of water, you might want to use a gram of water in an experiment versus 2 grams of water in an experiment. Okay, so then we need to account for different amounts. But for a calorimeter, the amount of stuff inside there is fixed. So there's essentially 3 different C's that we have to be aware of. A molar heat capacity, a specific heat, and then whenever we think a heat exchange is occurring inside a calorimeter, okay, and calorimeter information is mentioned, we can use CCal, all right, and the CAL is a subscript and it stands for calorimeter. We can use the calorimeter constant to take temperature information and make it energy information, right? So this is going to build, or this leads us to 3 different equations that we have for heat. Because remember, it's all about heat exchanges at this point of this chapter, all right? So we're going to label this section the 3Q equations. And essentially, because we have 3 different C's, we're going to have to be able to interpret what's given in a problem and take a C and get a Q. So for example, let's say we have a specific heat to start with. Now, a specific heat has units of joules per gram degrees Celsius, right? So if I want to calculate the heat, right, what are the units of heat? Well, heat is an energy, okay? So if I want to relate heat to C, and I kind of think about this as a conversion factor, well, heat's an energy. It has units of joules. So if I have a heat capacity, how do I just isolate joules? Well, grams is in the denominator. So what I'll have to do is multiply by mass. What else is in the denominator here? Degrees Celsius. So I would multiply by temperature, except, remember, we're going to be talking about making changes in temperature, okay? But a change in temperature, and I'll remind you, a change in temperature is a final temperature minus an initial temperature. Whenever we see a delta, that stands for change. And whenever we see a delta, that means a final value minus an initial value, okay? What would the units here be? Degrees Celsius. So degrees Celsius cancels with degrees Celsius here. The mass in grams cancels with the mass there. And what we're left with are units of joules. So this is our first Q equation. So when am I going to use this version to isolate Q as joules? All right. When you're given a specific heat and you see a grams in the denominator. Well, let's follow that exact same logic and let's develop our second Q equation. What happens if we're given a molar heat capacity? Well, hold on. Everything about it is the same except you're quantifying the object in terms of moles instead of degrees Celsius. So if I think about developing this Q equation, right? Well, if I have this C with the exact same logic, I need to get rid of moles. So how do I get rid of moles? I multiply by N. And how am I going to get rid of this how am I going to get rid of this degrees Celsius? By multiplying by a delta T. So the only thing that changes is what we multiply by to get rid of this unit, because again, if I have moles times C times a delta T, what am I going to isolate? I'm going to isolate joules. Okay. The last Q equation that we have is for those calorimeter problems. So when we see a heat exchange and we're also mentioning a calorimeter, right? When we have those calorimeter constants, remember, these are a bit easier to utilize because the C is just joules per degree Celsius. Okay, so if I was going to calculate a Q using this, well, I really only have to get rid of degrees Celsius. Remember, Q is an energy, it has units of joules. If I have this C that's joules per degree Celsius, what I have to do is take my C cal and multiply by my delta T. And when I multiply by delta T, degree Celsius cancels degree Celsius, and I'll be left with joules. So these are our three Q equations that we'll be able to use to solve problems now, all right? If we're given a specific heat and we see joules per gram degrees Celsius, we use equation number 1. If we're given a molar heat capacity and we see joules per mole degrees Celsius, we'll use equation 2. If we're given information that looks like we're referencing a calorimeter with a calorimeter constant or a specific heat for a calorimeter, all right, and I think Chem 101 uses the word calorimeter constant, all right, so if we're given that situation, we just need C delta T, equation 3, all right. So this is just an introduction into these concepts. There's one other thing that I'm going to mention that applies to every one of these equations, and then in the next video we'll do some examples together, right? In these three Q equations, there's a delta T. Now we pay attention to units, right? But there's one thing that's important to realize here in this chapter. Delta T in degrees Celsius is equal to delta T in Kelvin, right? Now remember from earlier in the semester, degrees Celsius, you have to take it and add 273.15 to get Kelvin, okay? So this tells me that degrees Celsius is definitely not equal to Kelvin. They differ by 273.15. But what about delta T, okay? So what happens if I have a T final minus a T initial, and I'm going to sort of show you, well, what happens if I have this change, right, which is our delta T, and I calculate it for measurements in degrees Celsius versus measurements in Kelvin? Well, let's take a simple delta T. Let's say we have 5 degrees Celsius and then 1 degree Celsius, right? So in this case, my delta T is 4 degrees Celsius. Let's look at the exact same change in temperature, but do so in Kelvin. Well, what do I do to this degrees Celsius to get to Kelvin? I add 273.15. So what I'll get is 278.15 Kelvin. Well, I have 1 degree Celsius here, right? So how do I convert it to Kelvin? Remember, we're just trying to monitor the same delta T, but one in units of degrees Celsius and the next in units of Kelvin, all right? But it has to be the same delta T that we're looking at, okay? So this would be 274.15 Kelvin. And if I plug that in my calculator, right, what we'll get is 4 Kelvin. So delta T's, right, if you're monitoring them in degrees Celsius, okay, they will equal the delta T in Kelvin. And this actually kind of makes sense. All this says is that degrees Celsius and Kelvin, they have the same spacing. They just have a different 0 point, okay? So if you looked at a degrees Celsius thermometer versus a Kelvin thermometer, the spacing on the thermometers would be the same. It's just the value that you would read would be different. So is 5 degrees Celsius the same as 278.15 Kelvin? Well, those things are equal, right? Because of this change. But numerically, they're different, right? They're different values, okay? But the difference between 5 degrees Celsius and 1 degree Celsius is the same difference between 278.15 Kelvin and 274.15 Kelvin. Now, this matters when we get to the next video where we actually start to do conversions and we start to do problem solving with heat exchanges and with just looking at quantifying heat. Because we have to be aware that it might look like we need to change from degrees Celsius to Kelvin, but, all right, if there's a delta T involved, the delta T in degrees Celsius is the same as the delta T in Kelvin. So next video we'll do some practical examples, the types of problems you'll see in Chem 101 together, so you make sure you understand how to use the Q equations and then also how to do a heat exchange problem or a calorimetry problem.